Okay, so there's a new branch in Geometry Nodes. So if you go to builder blender.org, search for branches, Geometry Node Simulation. So this is a new feature for 3.5 where you can sort of do, well, very simple simulations in geometry nodes. And this will be expanded in the future, so I'm just testing it out. And my goal for today was to solve differential equations. So I didn't download the branch, but I just compiled it locally, since I have that set up anyway. And so let me just go into Blender and show you what I've got so far. So if we just look at this part, there we go, and maybe set the resolution a bit higher. What this is doing is it's just making the exponential curve, so e to the x essentially. But some of you may know e to the x is the derivative of e to the x is e to the x itself. So it has a very simple, it's also the solution to the differential equation where the derivative of a function is equal to itself. And that's what we do here, is where we solve this differential equation. And as you can see, there's this node group f, which takes in the time and the given state, which in this case is just our x value, and its output will be sort of the derivative at that time and in that state. But for e to the x, the derivative is just the state itself. So that's why you can see the node group just returns the state, but you could put in a more complicated function there. So then what is the result of our simulation? So currently I'm on frame 1, but if I press play, you can't really see it because this, let me put the resolution of this to 2. You can see, you can see that it's sort of solving the differential equation iteratively in the simulation, and that generates this exponential curve. Now currently it's using the Runge-Kutta method, but let's see, we go for the more simpler Forward Euler method, so I'll go a bit more into detail what each of these are. And we start from this beginning. You can see it looks pretty good, but as you can see, it's sort of off. It's like not that good as when we did it with the Runge-Kutta method. And this is sort of first order approximation, and this is a fourth order approximation, so that's much better. But as you can see, the node group for Runge-Kutta is quite complicated, while that for Forward Euler is extremely simple. So there's that. Now let me go over a bit how this works. So first we create just an object, just a point cloud with one point, because we need some geometry. Currently the simulations only, we don't have actual loops, we just have simulation, but I'm using it as a loop. And that needs geometry to work on. So that's why I just create geometry, and that's where we'll store our attributes, which are sort of like our variables that we're iteratively updating. And then I set up the initial state. So for the x value, this is, well, I guess like the x value here, and then the z is sort of the value of e to the x at that point. So for x equals 0, e to the 0 is equal to 1, so that's our initial state. And then I also store that as the position here, and then I store this in a named attribute named state. Good. So then at the start of each loop, take in the geometry from our previous thing, and we get the state out. That's what this sample index does. and we just store the state on the whole geometry, so it doesn't really matter what index we use here. Then we take that state, and then remember the x was sort of like the time, or the value along the x-axis, while the z value was the height. So we pass those into our forward Euler, and we also need to know the time step, like how much do we move along the x-axis at each step. So in this case I've set it to 0.1. If I set it to something like 0.01, and maybe increase this to like 200, you'll see what happens. It goes in way smaller increments. But the result in the end will be much more accurate. Like the final result that it calculates will be more accurate because it had more time. It had much more sub-steps. Good. So let's just skip over what happens in here now, but we can sort of, this calculates the next time step, or the next point, and the next value, or our new state. So it sort of updates the time and the state. That's what this is responsible for. Then we create again a new point just to store our state in, and we set the position to that, and then we store a named attribute with our current state on the geometry. So these points are for keeping track of the positions we had throughout time, and this is for keeping track of the current state. Okay, so then at the end of this, what happens is on the next frame, the output here goes back into the input here, and we repeat the process. So frame, let me, okay, so it's set to this. So we go here, so we've done our first thing. Now the output is back. We calculate the next step, we place a point there, and we get our next point, and so on. So each step we calculate, we use the function gives us the derivative, so we know the slope at that point. Then we just use the slope to get to the next point, and the next point, and the next point, and so on. And then in the end what I do here, so we have all our points, then I just use these points with their positions to make a nice smooth curve using a mesh line, but I could have used a curve line node here as well if I wanted to. For example, use curve to mesh afterwards. Might even be better. And I just transfer the position attribute that we stored on each of the points to this curve, which is what you see here. So if I rid of that, or just add the other thing, then you would see all these points here. I should set the radius to like 0.01. As you can see, it's not updating immediately. That's because you would have to restart the simulation. So I go to the first frame. You can see those are the points that we're adding. Maybe I should set this to even smaller. And maybe that helps to visualize what is going on. And then in the end I just join this with the sort of actual curve that we know for sure this is what the exponential should look like. But if the resolution, currently the resolution is only evaluating it at the start and the end, because there's only 2 points, but if we set this like 150, we let our simulation run. As you can see, it is quite accurate. It's not perfect, but it's not far off either. But remember, this is the sort of naive forward Euler approach, and the Runge-Kutta method is much better. So if I do the same thing again, I'll let it run. As you can see, like a while ago we were here, and now even no matter how much I zoom in. Like I have to zoom in so like pretty much to the, like I can't zoom in, Blender doesn't allow me to zoom in any further, so it's almost to floating point precision already. So that just shows how accurate or how much better this Runge-Kutta is. And this is quite well-behaved differential equation. For more complicated differential equations, the difference will be even more noticeable. So how do these work? Well, think about it. I'm gonna set the step to something much bigger, like 0.1 or even 0.4. And let's go here. And I should use this. There we go. So, and yeah. So as you can see at the start, we start off at this point, and the only thing that we're given is this f, which calculates the derivative at that point. So we know the derivative or the slope of the curve at that point. Well, then what would be a good estimate if we wanted to know at, say, like the next point? Here, if you wanted to know the value of the curve, we can just use this slope right here. And so we know how much we have to move along this, along the x-axis, that is our time step. And then we use that times the slope to know how much we need to move along the y-axis, sort of by definition of the slope. But as you can see, the result we saw was decent, but it sort of undershoots, because each time, like it's calculating the slope at the start here, but then obviously if the function is increasing, then this slope would be like it's not accurate over the whole span from like going from here to here. Like here the slope is already more, so like it should have increased more. And Runge-Kutta method does that a bit better. So what it does, as you can see with the exact same time step, the result is pretty much spot on. What happens is Runge-Kutta first calculates the slope here, then goes halfway using that slope, so it gets around here, let's say, and then it evaluates the slope again at this point. Now it's maybe not exactly on the curve, but it's gonna be pretty close, and then that gives it a new slope, which it then uses again starting from here to get even closer to the curve, and then calculates the slope again, and then final time uses that slope to get over there, calculates the slope there, and then takes a weighted average of those four slopes. So on Wikipedia page for the Runge-Kutta method, there's a sort of nice graphic here that illustrates this. So you calculate the slope here, that's the K1, then use this slope to go to like the half of your interval, calculate the new slope there, use this new slope, calculate again the same on the same spot, but now using this new slope, so you'll end up over here. You get this K3, then use this final K3 starting from here, calculate the slope at the end point, which will be your K4, and then you take a weighted average of these four. So this is this 1/6 K1 plus 2 times K. So the center ones are more important or get a higher weight than the end ones. So that way it's more consistent over the whole interval. Well, like if you look at Forward Euler, it just looks at the slope at the start, which is sort of naive, if you could say. And you can see like this example that they give here, where like the red one is the exact solution, the Runge-Kutta is the orange ones, or the greenish, brownish ones, which are really good. And then the Forward Euler is like, it's way off, as you can see. Like it's just not good. So there you go, learned something new. Now my goal, now convert this setup that we have into a setup for solving the Lorenz system, and that's one is given by 3 differential equations. So here we have for the Euler equation, for the, should I say, the exponential curve, we just had one differential equation. dx dt is equal to x. That was it. It's like the derivative is equal to itself. Here we have sort of 3 variables, which you could see as a position x, y, and z. And we know that at each state, so let's say we have a given x, y, and z, then derivative at that state along the x-axis is given by this value, so some constant sigma times y minus x, so the y of the current state minus the x of the current state, and so on. So these 3 will give you sort of the derivatives along each of the axes, and then you can update these on and on, using, for example, Forward Euler method or Runge-Kutta method to get like a path through time. And for some values you get really nice patterns, like for example if you use these as the constants, you get these nice butterfly shapes. Or like here in the simulation you can see that it looks really cool. So that's the goal, and let's see how well we can do. So one thing I already noticed is we have, instead of just 1 variable, we have 3 variables. So, and we also have to keep track of time, so we'll need an extra store named attribute node here. Let me first save this as a new file. So let's call this Lorenz system. Okay. Now we won't need this ground truth because we don't know. There's nothing like the exponential where it's a known curve. I could leave this so we see both the points and the things. Alright, so let's start off. So we have our state, and we also have our time, which is going to be a float. And we'll start with t equals 0. Yeah, what I saw they, like, does it say here? So 28, 10, 8 over 3. So 28, 10, and 8 divided by 3. Okay, that's our initial state set up. Okay, so now we grab our state. Now we'll need to update these node groups. Let's first do the Forward Euler one, because that will be easier to update, because there's less stuff. So instead of taking just state as a single value, this state should be a vector. And this should also be a vector. And if you go here, then this should also be a vector. And a vector. Okay. So maybe let's first update our function. So let's put this here. So we know oh wait, I think I made a mistake already. Yeah, this is not our initial state. These are the values we use here. So let's just set our initial state to all zeros for now. We'll see later if there's a specific value they recommend on the Wikipedia page. Alright, so let's add inputs for sigma, rho and beta. A value, let's call this sigma, let's call this rho. So if you don't know, those are the Greek letters, the sigma, rho and beta. And finally, let's add beta. So what was it they recommended? It was like 20. Let's see. So rho is 28, sigma is 10. Rho is 28, sigma is 10, and beta was 8/3. Now we can change these later if you want, but I think this will probably give us a good solution. Okay. So I guess we'll need a separate XYZ and also a combine XYZ. So as you can see, like the value of t doesn't appear in the differential equation, so we won't need this t value here, but there are differential equations where it does appear. Okay, so our x value becomes sigma of y minus sigma times y minus x. So let's add a we could do this in one node, I think. No, that's not true. So let's say just subtract. So it's y minus x. And then we multiply the result with sigma. Okay. Let's just put this over here and swap these around. Okay. Now, secondly, the y value is x times rho minus z. So let's do rho minus z. So subtract z. So we have rho minus z. We multiply the result with x. And then we subtract y. Okay, that works. And then finally we have x times y, so we'll just copy this, take our x times y, and then we subtract beta times z. So z. So I should put a multiply here. Multiply beta by z right here. And then we subtract that from x times y. This should be our z. Okay. So that gives us our updated function. And now we just need to change this, I guess, to vector math node. So remember, this is the slope. So we take our initial state, multiply, it should be multiply add probably. We take our original state, and then we take our new state, which is gonna be, well, new state is also the slope. So it's not really the new state, but then we multiply it by the time step, which is this dt. So, right, we've got our slope, we've got our x offset. So we multiply the slope by the x offset to get the y, and we add that to our previous state. That's what we have here. And then we just put this here as new state. So I guess the result of this the name of this shouldn't be state. Should be derivative, if I can type. Okay, so I'm fairly confident that this should work. Almost, actually. So this is wrong. So we need this should just be here, and then we need another one of these to grab the float. Named attribute, oops, and this one I'll call time, or I called it t. Yep, so we grab our t, we plug this into here. Okay, and then here we should give our new state, and then our t value, we should also store that in another named attribute. So I'll copy this, change this to float. The reason I'm using named attributes is because we don't have like a way of outputting an attribute to the simulation output and then getting it back from the simulation input. So if we could do that, then I would use that instead, because it's much easier than working with all these named attributes, in my opinion. Okay, so let's run this. And that doesn't look good. So I'm not sure if it's actually doing anything. So the initial state, let's see, what state did they use? For example, here, initial state was 1, 1, 1. Okay. So, okay, let's maximize this again. Let's see, is it actually computing points? So it is making points, so it should also make some geometry. But I don't see it, which is weird. Okay, now I do. So probably there's some mistake somewhere. Let's have a look. Let's also make the time step much more. Well, this looks... Well, there we go. That does look sort of like the image. But it was just a time step which is way too big, especially for Euler. So let's make this like 1000 and let's change the FPS to, let's see how high it can go. we could try it with different inputs, but I'm gonna leave that for you. And I'll put a link to this blend file so you can play with it, and also the one with the exponential curve. I'll put a link to that one as well in the description so you can play with it yourself. You don't have to copy everything hand by hand, but you know, do make sure that you are on this, again, to builder.blender.org, that you go to branch and you select this geometry node simulation branch, or if you watch this in the future that you're on like Blender 3.5, if it's already merged into master, so that you have access to these simulation nodes. Alright, hope that was useful, and I'll see you in another video.